All right, so you do have 5 questions. I think there's one on there that's like this. Um, we'll do example 11. It says solve dz dx equals x cubed ln of x if z equals 5 when x equals 1. Okay, so first of all, we have to read the question and understand what it is we have to do, because you can have all these skills develop. Like, man, I practiced doing this 100 times and I'm really good. If you tell me to do that, I can do that. But no one's going to tell you to do it. You have to know, oh, this is one of those times where I need to do that, right? So first of all, it says to solve, and you have an equation with a derivative in it, right? That's solving a differential equation. So solving a differential equation means getting back to the original function. This is a first order differential equation because it's a first derivative. So all we have to do is find the antiderivative one time to get it down to z equals. That's what we're trying to do, get it down to z equals. Now, let's look at it. Your independent variable is here, and that's all the variables you have on that side, right? So notice this one doesn't necessarily say solve the separable differential equation. If there were any z's on the other side, you would need to make sure you separate them. Now, if you want to solve it, feel free to do the same thing. Let's just multiply both sides by dx, and we'll just stay in the habit of separating the variables now, okay? But that's really just a 1 left over here. And then we'll sneak the integral symbol in. So this is like an extra step that we didn't do back in the day before we didn't have separables. We just went straight to here. What would be the antiderivative essentially of what is a 1 with respect to z? X, right? But with respect to z, it's z, yeah. Okay, and then over here, we have to integrate x cubed natural log of x. Well, crap, that's a product of 2 variable functions. Does one of them have an inside function whose derivative is the other factor? No, crap. So this is where you have to be like, all right, I could do this. If you ever have powers of x or polynomials for that matter in the presence of, okay, let's just say this. If you have x to the n, and then the other factor is either like ln of x, e to the x, sine of x, cosine of x, arctangent of x, any of that stuff with respect to x, guess what you're probably going to have to use? You're going to have to integrate by parts. Yeah. You're going to have to integrate by parts. Now, your first choice, okay, choice 1, your first choice is to let u be the power of n, okay? Why would we want that to happen? Because eventually you're going to get down to u prime or u double prime, well, let's say, and you get down to 0, okay? It would be u to the n plus 1, really, but that doesn't always happen, right? And what does that mean then? If you do that, then dv has to be the one that you have to integrate. U is the one that you take the derivative of, but dv is the one that you integrate. So let's say if you did that here, if you let x to the n be u, would we know how to integrate natural log of x? Do we know how to integrate natural log of x? Not unless you memorized it, no. We only know how to take the derivative of natural log of x. So this forces your hand the other way. But if I let x to the n be u, e to the x could be dv, because I can integrate e to the x. Sine of x I can integrate. Cosine of x I can integrate. So these are going to be your option 1. Okay? But notice the natural log of x and arctangent of x, I only know how to take the derivative of those. So that's going to be your choice 2. Okay, is to let u be the one that you can actually take the derivative of. It forces your hand the other way. And then dv is going to be x to the n. And that's going to happen when, let's see, I'll use blue here, right? Choice 2. That's going to be those 2 right there. All right. And if you got that down, then you can use the tabular method. Works every time. pretty much, if you've done enough of these, and I don't know how much you've done in the last few days, but the exponent on the x kind of tells you how many iterations you're going to have to do. So if you have a power of x that's greater than 1, you probably want to use the tabular method. Okay, I would just say that right here. If n is greater than or equal to 2, let's say, use the tabular method. Okay, otherwise you can use the zero method. Hank, you might want to retake the picture now. Yeah, retake the picture. All right. Yeah. All right. So that's kind of like a rundown of integration by parts strategy. Okay, how to recognize it and which choices, but now we have to know how to do it, right? So let's go ahead and off to the side on my workbench. I'm going to move this stuff over here. I need the space. Sorry. Okay. Now on my workbench, I don't want to keep working down here in the project. So I'm going to go off over here to my mathematical workbench. Happy World Math Day, everybody, by the way. World Math Day. It's also National Puppy Day. So that's good too. U, dv, plus or minus. So these are the 3 columns. And I'm doing the tabular method because the exponent on the x is what? 3. And I don't want to have to do 3 backward Zorro methods because that's going to be too hard. Okay. You can use the tabular method every time. Now, I would like to have u be x cubed, right? Because that would be 3x cubed. And then I just take the derivative of 3x squared, take the next derivative of 6x, 6, and I hit 0. That'd be nice. But now that means that at ln of x has to be dv. And what would be the antiderivative of ln of x? We don't know it. We don't know it. It's x minus x ln of x, but ooh, no, we don't know it. So guess what? Oh, this is where we have to force our hand the other way. So ln of x, okay, you win. You win ln of x, fine, boom. And then, of course, like we get up every morning, we start with a positive, right? It's a great day to get up and get them. All right, and then you hit snooze. All right. Today I did hit snooze, I have to admit. I'm sorry, I did. It went off way too fast. All right, so now let's go down. The derivative of ln of x is 1 over x. Now, if you keep going, you're not going to hit 0, are you? The root of 1 over x is negative 1 over x squared, and then, yeah, 1 over x. It's not going to happen. So you don't need to go ahead and start just getting your columns all going. What would be the antiderivative of x cubed? 1/4 x to the 4th. You don't need to put your plus c in there, and then we'll put a minus. Okay, so now you alternate signs down that column. Now let's see if I need to even go further. This is how you deconstruct the tabular method. It's always going to be the first diagonal's product. You multiply. So now I can come back over here, and the integral of that is going to be x cubed times 1 over x. Okay, always. And then minus the integral of the horizontal product. That's how you tie it off. Did y'all see in the video or hear me talking about tying off the tabular process? Yeah.
You went ln of x times that one.
Oh, did I go the other way? Oh, I'm sorry. Yeah, you're right. I'm sorry. It was a long night, long plane night. Sorry. I got my diagonal backwards. In the video I did this way. Yeah. ln of x. Yeah, that's right. It's this diagonal. Sorry. My bad. Because the backwards z would be like this. My bad. There's the backwards z right there. Okay. I'm sorry. Z has I did Z, right? And I didn't want to do Z. Z right now has like that stands for like Russian invading Ukraine. It's backwards Z. I don't know. Backwards Zorro. All right, so my bad. So the horizontal line just restates the problem. That just restates the problem. So now you take the first diagonal, which is ln of x times 1/4 x to the 4th. And then now you tie it off. you tie it off with the horizontal line and an integral. And if we went down another diagonal, then it would be plus, right? You always tie it off with that same sign, but you tie it off with an integral. And now we tie it off with the horizontal product, which is 1 over x times 1/4 x to the 4th dx. So even though I wanted this to expire down to 0 with x cubed being u and just product, it couldn't do that. So that's how you tie it off. Now, the way that these problems are designed is you'll be able to do them. So I'm not going to rearrange this. This is 1/4 x ln of x. And now look what happens here. When I simplify this, this becomes minus 1/4 the integral of x to the what? 3rd, right? And now, yeah, because this is 1 over x times x to the 4th. Did I? Oh, it's x. Yeah, I'm sorry. I'm just really messing this up. X to the 4th, x to the 4th. And then there's dx. Thanks, guys. Y'all are so tolerant. Sorry, it's been like 13 days since I've done math. Right, I've been taking picture mode, but details matter, right? Details really matter. So backwards Zorro, tie it off. And the way these problems are designed, what I was saying is you'll always be able to simplify that new integrand into something that's manageable. Now, you don't have to worry about the plus c, because technically that first part is partially integrated. You don't have to worry about the plus c until you finish that last integral. So now it's minus 1/4, and then x cubed becomes 1/4 x to the 4th, close parentheses, plus c. That's when you put it, when the last integral disappears. And of course, then you can simplify it to 1/4 x to the 4th, natural log of x, minus 1/16 x to the 4th plus c. And this is called now your general solution, right? Your general solution. How do I find the particular solution? I have to plug in the point. Wow, this is a pretty intense problem. When x is 1, z is 5. So the ordered pair is 1, 5. I'm using z instead of y essentially. So now we'll say at 1, 5, colon. That's probably the easiest way to show it. You plug it in. Let's see what we get. And again, this should work out to something relatively nice. You plug in a 1 for x and you get 1/4 times the natural log of 1. Hey, what the heck is the natural log of 1? 0. So that whole first term is gone. Minus 1/16 times 1 is 1/16 plus c. And now all I got to do is solve for c. And you get another check for there. Is to add 1/16 to both sides. So 5 is how many 16ths? 80. So 80 16ths plus 1/16. 81 16th. What a fantastic c value. So, and now we plug it back into the general solution. The particular solution is z equals, or z of x, if you want to make it a function, 1/4 x to the 4th ln of x minus 1/16 x to the 4th, and then plus 81 16ths. Tedious, right? Tedious. But the method is still the same. So this is good because this is a review of solving separable differential equations. But in this case, the integral required a new skill, which was integration by parts. All right, questions on that one? Tie it off. You always tie it off with a horizontal product and an integral symbol, whatever that sign is. Okay. Let's do example 12. Is that what we also said we do that? Yeah. All right, let's look at example 12. If f of x is x cubed cosine of dos equis, find the average value of f on the interval from 0 to pi half. All right, find the average value of f. Average value, average value, average value, average value. It's not average rate of change. Average rate of change is secant slope. That's algebra 1 slope. Y sub 2 minus y sub 1 over x2 minus x1. That's average rate of change. This is average value. How do we find average value? Integral over width. Yeah, integral over width. This shows up a lot. Integral over width, integral over width. It's the density method, okay? So let's go ahead and set it up. I'm going to say that the average f value is the integral from 0 to pi halves of x cubed cosine of 2x dx all over the width pi halves minus 0. Now in a free response, which is how I kind of do all my examples as if they're free response, that's a check. You should get in the habit of labeling your integrals as well. You can just put average value, or you can put average f, whatever, or just average setup. Okay, so if you wanted to clean that up, you could put 2 over pi in front of it. But let's focus on the integral. X cubed times cosine of 2x. That's a product of two variable functions. Does one of them have an inside function whose derivative is the other guy? No. Now, look at this. This could be the inside function, 2x, right? But what's the derivative of 2x? 2, not x cubed. Crap. Now, what if that had been 2x to the 4th? Then would we have been in business? Then we would have been in business, because then it just would have been, we're off by a constant multiple. The antiderivative of cosine of blob is sine of blob. But that didn't happen. So does it fit this format up here? A power of x times one of those dudes? It sure do, right? So off to the side on my workbench, and you don't have to label the workbench, but I will. I'm going to focus on the integral part. Now, again, here's your columns, u, dv, plus or minus. The power of x is 3, so I don't want to have to do a Zorro method 3 times. I would really like to do this as x cubed. Again, the power of x is what I'd like to call u, because if I take successive derivatives, 3x squared, 6x, 6, and 0, I can just keep doing diagonal products, and 0 times anything is 0, and then I'm done. I know when to stop. But if I call u x cubed, I would have to call dv cosine of 2x. And I can only accomplish that if I know what the antiderivative of cosine is. Do I? Boy, howdy, do I. And that's why these fit this mold right here, because we can keep going successively with antiderivatives of sine of x and cosine of x, and especially e to the x, right? All day long. All right. Now, don't take this for granted. Every time we integrate, we're going to have a correction, aren't we, of another 1/2? So don't just forsake the inside function. So the derivative of 2x is 2. There's not a 2 outside. So we have to have a correction of 1/2. And then the antiderivative of cosine is sine of 2x. Okay. Now, in this case, if you tied it off horizontally, like if you did the backward Zorro and you tied it off horizontally with a minus the integral, are you going to be able to integrate x cubed times sine of 2x? No, you're going to be in the same boat that we started with, except with x squared instead of x cubed. So that's how we know not to tie it off. When you can hit 0 in your u column, you just keep going. So there's a minus. The next antiderivative is 1/4. Well, what's the antiderivative of sine of blob? Negative. So I need to put a negative there, cosine of blob. And on the next integral, I'm going to be off by a 2. So I have another correction of a 1/2. So it makes it 1/8. And the antiderivative of cosine of blob is sine of blob. So it's still negative, right, from above. And now the last one, I know I'm going to be off by a 2. So I have a correction of another 1/2. And what's the antiderivative of sine? Negative cosine. So it actually turns back to positive 1 cosine of 2x. Oh, and by the way, I forgot to do my plus minus along the way. No big deal. Just alternate. Plus minus, plus minus, plus. All right. Always start with a positive. Yeah. Restroom. Oh, freshman center. Oh, yeah. Feel good. Feel good with those freshmen down there. Tear them up. Tear them up. I'm recording right now. So bye, Ethan. Bye, Brody. Hear yourself on the announcements. Well, everything I say you can think of as an announcement. I'm announcing math. I'm still not in the groove. Y'all have fun. See ya, I hope. Yeah. Plus minus, plus minus, plus minus, right? Okay. Let's go ahead and list it out now. I'm going to come over here and I'm going to say the average value is dividing by pi over 2 is the same as multiplying by 2 over pi. And now I'm going to put a beefy bracket. All right, so here we go. Here's the first diagonal. and it's positive 1/2 x cubed. I'm going to rewrite it as I put it down. 1/2 x cubed sine of 2x. Okay, now you go across and pick up the next sign, minus. So it's diagonally and then across. Now we got the minus, and then here's your next diagonal. Well, it's negative 3/4. So what does that do to that negative sign? It makes it positive 3/4. It's tedious, but it's nice. And then you have x squared cosine of 2x. And then you go across and pick up the next sign, which is positive. And then you come down on the next diagonal, but wait, it's negative, right? So a net positive times the next. So now we get negative 6/8. That turns to negative 6/8. X to the first, sine of 2x. And then you go across and get the minus. And now it's the next diagonal again. 6 times 16, and it stays negative, times cosine of 2x. And then look, we go across and get plus. But what happens on the next one? 0 times anything is 0. So at this point, if this had still been a minus instead of a plus right here, we would probably change it to plus and put plus c. Okay. You could technically put minus c, but is that what we want to do here? No, not really, because this one actually ends up being a what? A definite integral. Aha. So now we close the beefy bracket and we evaluate it. Are you serious? Yep. March Madness, baby. From 0 to pi halves. Whoo. But if it were just a general, you could put plus c at the end. Okay, now we need to evaluate it. So again, I'm just keeping the 2 over pi out front. There's the bracket. I'm going to put a parenthesis now. When I plug into pi halves, let's be smart about this. Every time I plug into pi halves into the angle, I'm going to be doubling it. So I'm really going to be evaluating sine and cosine at pi, right? So what is sine of pi? Sine of pi is 0 because sine is the y, which is the height. And at pi, it smashes down to a height of nothing. And what's cosine of pi? No, negative 1. Yeah. Okay. So let's go ahead and plug in then and simplify as we go. So when I plug it in, I'm going to get sine of pi, which is 0. So this whole first term is gone. Plus, if I plug it in here, cosine of pi is negative 1. So that's going to turn that into a negative 3/4. Yeah, because I'm going to get a negative 1 there times the 3/4. So that's a negative 3/4. But then I got to square. I got to square the pi halves. So I'll just put that as pi halves squared. All right. Now we'll plug in the next one into sine. And guess what? It's going to be sine of pi again, which is minus 0. And then we plug it in and we're going to get plus, because it changes the sign, 6/16. That's plugging in the top. Crap. Minus, parentheses, plug in the bottom. Well, now when we're plugging in a 0, what's sine of 0? It's 0. And what's cosine of 0? Positive 1. So it's very similar now, right? When I plug in a 0 to the first one, I'm going to get 0. But now I'm going to plug in a 0 and get 1 times 0. Well, ooh, there's an x. So that's going to be plus 0. But it's made 0 by the power of x, not the trig function. And the next one also has a factor of x, so it's 0. And the last one, cosine of 0 is 1, so it becomes minus 6/16. Well, that was nice having an x factor in those first 3 terms. Now, of course, when we simplify, the 6/16 end up doubling. But is that a numeric answer? Is that an okay place to start? Yeah, yeah. So is this question a BC caliber question? No, it's probably a step outside there. It's a right. They might ask you to find the average value, but they might give you x instead of x cubed. So I just throw all these things together to review you, right? Average value is integral over width. We got unit circle in here. We got tabular method. We got it, right? Okay. So that is tabular method. Now this one here, evaluate e to the x over secant of x. This one is not going to be on the AP exam. Y'all want to see it? Yeah. Now it's a quotient. What do we typically do with quotients? We write them as products, right? So there's two ways to bring secant to the top. You can bring secant to the top like this, of course, right? Leave it in terms of secant. But now what's the derivative of secant? Don't tell me e to the x. Ah, crap. Criminy. Okay. So that one's not going to help. What else can we do? If I bring secant to the top, I can call it its reciprocal function, which is cosine. All right. Now, that doesn't really help me either, because now I have a product and the derivative of, there really is no inside function other than x, whose derivative is 1. But this one has a double repeater. A double repeater. A double repeater. Repeat means to say again. So a double repeater would mean to, wow, say it 4 times. Yeah. All right. And by repeater, I mean this right here. The e to the x, sine of x, and cosine of x, they get caught up in a cycle, right? They're cyclical. You can keep going indefinitely. So whenever you have a double repeater, this is not BC. It is an interesting thing. Okay. Let's come down here. What you have to do is you have to keep it in equation format. So on the left side, go ahead and write the problem. You'll like this one. It's worth showing you. A lot of stuff in DC was closed. You couldn't see a lot of stuff. This is one of those things that was closed, but y'all have access. Y'all have like, I'll let y'all in. I'll let y'all in. Come on in to the intersectum. DC calculus, right. All right, so let's come over here. We got U, dV, plus or minus. And let's see, when they're both double repeaters, dang, which one do you want to call U? Does it matter? I could take the derivative of both e to the x and cosine of x, no problem. And then dv would be the other. Well, I know how to integrate e to the x and cosine of x, no problem. So in this case, you actually have your choice. You know what I'm going to choose for you? Cosine of x. You know why? Okay. I mean, you can have your whatever reasons. I'm going to choose it as u because when I take the derivative, I'm less likely to make a careless mistake. I know if it has a co in it, it's going to be a negative derivative. Sometimes when I'm integrating, like the integral of cosine, is it sine or is it negative sine? Sometimes I can mess that up. Okay, now let's go ahead. I'm going to take the derivative of the left side. Derivative of cosine is negative sine. The antiderivative e to the x is e to the x, and there's a minus. So we know we're going to take the first product, right? So this restates the problem. We take the first product. So I'm going to come over here. It's equal to e to the x cosine of x. Okay. Now, here, when are we going to stop? Well, I don't know. Let's go to the next. Minus. Well, let's keep going. The next column will be negative cosine of x, and the antiderivative e to the x is e to the x. So the next product was going to be this, right? Oh, I don't know. It's not. Why is the x at the top? Oh, crap. That is, oh, that's good. That's good. I don't know. Yeah. 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 It's the new letter, right? Cosine. All right. So first diagonal and then minus, and then we pick up the next diagonal, which turns it to plus e to the x sine of x. And then I'm going to come across here and get the plus sign. Well, when do we stop? Here's when you stop. You stop whenever your horizontal product gives you the same product that you started with, okay? Which is this line. You see that? If I were to tie it off here with a horizontal product, I would end up with an integrand that's some type of e to the x cosine of x, okay? So here I will tie it off on the next line, which I go to plus. I tie it off to plus, and then it's going to be the integral of negative cosine of x e to the x dx. I tied it off, and if I didn't tie it off, it would go. I would have products forever and ever, right? It would never expire. Neither one would ever expire. It would just be product. So we have to tie it off. Now here's the insight. You can always see on the back end when you look behind the scenes why it works. By having my integrand as the same product, notice it's minus. I've turned this into an integral equation. I can do some algebra now. I can take this negative term and red rover, I can bring it over to the left-hand side. And what would that do to its sign? It's negative right now. You can bring the negative out front if you want and turn it into minus. It becomes plus, right? And then I'll have one of those plus another one of those, which makes how many of those? Two of those. Those can be anything. It happens to be those. I have two of those now on the left, and on the right, I have e to the x cosine of x plus e to the x sine of x. And because the integral is gone, guess what I need to do? I need to put my plus c. They really should all have their own plus c, remember? But you're not going to lose points, okay? But with the integral gone, you need the plus c. Yeah.
How is it equivalent if you would subtract that from that?
Well, it isn't, well, it's negative, right? If I want to bring that negative out front, I'll just turn it in like that. How does that look? Instead of having a negative in the integrand, I have a minus sign. So I'm going to add it here, and I'm going to add it here. Right? So what happens over here? They cancel out to give me 0. And what happens over here? I have one of them plus one of them.
Yeah, but you had a positive, so I was wondering. It was a plus.
Oh, because the negative was in the integrand. Yeah. Yeah. I had the negative on the other side of the integral symbol. I'm sorry. It was there. Hi, Coach Fair. That's Coach Fair, everybody.
Guys, watch this. How are you? Good, thanks.
Okay, good. Yeah. Yeah. Nice. Now remember, what were we after? Never lose sight of your target. I wanted to know what the integral of e to the x cosine of x is. How do I solve for that on the left? How do I get rid of multiplying by 2? Divide both sides by 2. So your answer is the integral of e to the x cosine of x dx is everything on this side. All divided by 2 if you want, or if you prefer, put a 1/2 in front of the whole thing. Or if you want, distribute the 1/2, 1/2 e to the x cosine of x plus 1/2 e to the x sine of x. And then what is 1/2 times c? ShamWow c. Yeah. So any one of those could be answers. There you go. It's a double repeater.
So we know when to tie it off whenever it gives you the same product as the first line.
Whenever your horizontal product gives you the same thing as your original integrand. Yes, right. Yeah. You're not going to see this in the BC exam. Yeah, on the BC exam, either the left column expires to 0 and you just take products all the way down, or you're going to do like one iteration. It'll be backwards 0. Tie it off after the first product. Yeah. Yep, that's right. And then that whatever is left behind the integral will simplify to something you can do. That's exactly right. So that takes care of integration by parts. Comments, questions, quips, quotes, concerns? Yes. Yeah. Turn in the what?
There's an assignment for like Monday and Tuesday that was due last night.
No.
Was an assignment, but then it changed, so we don't actually have to turn it.
No, you don't have to turn anything in. No. It was confusing. Again, I was trying to communicate through Canvas with my iPad, which is bad. So nothing for Monday and Tuesday. Here's what I want you to be able to do. If you go back through and do your notes, I added these in Canvas. So here's the notes for 5.4. And in there, I put the YouTube links because here's the deal. I take so many pictures. My Android phone, which is 128 gigabytes, was running out of storage. So my phone nicely said, hey, everything is backed up on Google Photos. Everything is backed up on Google Drive. You want to delete some of these off your device? And I'm like, yeah, I need to take more photos. So when I did that, it went in, and for some reason, I guess there was some box check somewhere. It got rid of all of my videos in the shared folder, except this year for some reason. So the previous 4 years that I had, all those videos that go further and further into the notes, they're gone. So that's why when I linked it to y'all at first, to previous year's videos, it sent you to a blank folder. And I was a little bit upset. That's 4 years of work gone. But all of those videos, not all of them, but at least one video of each section I have on YouTube as well. They're just not easy to find, as easy to find. But I found these two. And so that's why I gave Mrs. Lincoln the link. Y'all can't watch them on your iPads at school. So I wanted either her to download them with the other link I gave her and put them on the desktop for the sub to hit play, or press play on my computer, which does have access to YouTube, and show them to you. So bottom line is, if you're not squared away with the notes for 5.4 and the optional worksheet, we'll still stick with optional worksheet. And then I put it here, the notes for 5.5 now with the two links. And what we've done now is some of this as well. Make sure you get 5.4 and 5.5 squared away. Okay, because tomorrow I want to start 9.1. Now I'm going to stop now and we're going to take a look at 5.5. Okay.